The same food does not taste the same everywhere. The ingredients can be identical, yet the experience shifts. It feels like preference. It is not. Taste appears simple. You put food in your mouth. Flavor happens. You decide whether you like it. But flavor is not located in the food. It is constructed in the brain. Within seconds of chewing, your tongue detects only 5 primary categories: sweet, salty, sour, bitter, and umami. These signals travel through cranial nerves into the brainstem and then to the gustatory cortex. That is the chemical core. Everything else, richness, freshness, depth, nostalgia, comfort, is built from additional systems layered on top. Smell contributes the majority of what you call taste. Volatile molecules travel retronasally from the mouth into the nasal cavity. Without this pathway, flavor collapses into basic taste. This is why food seems dull when your nose is blocked. But even smell is not enough to explain the difference between locations, because flavor is multisensory prediction. The brain does not passively receive taste. It anticipates it. Before food reaches your mouth, visual input has already shaped expectation. Color influences perceived sweetness. Plating influences perceived quality. Lighting alters contrast and saturation, subtly shifting how ingredients are interpreted. Context begins modifying flavor before chewing begins. Then comes sound. The acoustic properties of a space alter perception. Studies show that higher frequency ambient noise can enhance perceived sweetness, while lower frequency noise can enhance bitterness. Crunch is amplified by auditory feedback. The brain uses sound as evidence of freshness. Location changes sound. Air pressure and humidity also influence aroma volatility. In higher humidity, certain aromatic compounds linger longer in the air. At altitude, reduced air pressure alters both smell sensitivity and the boiling point of water, subtly changing cooking chemistry. Even carbonation behaves differently. Location changes physics. Then there is memory. The hippocampus and amygdala link flavor to emotional context. If a meal is consumed during novelty, relaxation, or social bonding, dopamine release enhances encoding. The food becomes associated with that state. When you eat the same dish elsewhere, the chemical composition may match, but the predictive template in your brain does not. The mismatch reduces perceived quality. This is not sentimentality. It is neural calibration. Flavor perception depends heavily on expectation. When expectation is high and confirmed, reward circuits amplify pleasure. When expectation is unmet even slightly, the reward signal weakens. Travel intensifies expectation in 2 opposing ways. Novel environments heighten sensory attention. The brain increases dopamine in response to unfamiliar stimuli. Colors seem sharper. Smells seem stronger. Experiences feel amplified. Food consumed in this state benefits from heightened neural gain. At home, the same food competes with familiarity. Predictability reduces dopamine response. The sensory system becomes efficient rather than attentive. Efficiency feels like dullness. Social context compounds this. Eating with others activates reward pathways independently of taste. Oxytocin and dopamine modulate perceived pleasure. Meals shared in meaningful environments feel richer, not because of seasoning, but because of neurochemistry. Remove the environment and the chemistry shifts. There is also effort. Effort increases perceived value. When food is obtained after travel, planning, waiting, or navigating unfamiliar streets, cognitive investment rises. The brain interprets effort as evidence of importance. Importance enhances sensory weighting. The same dish ordered casually at home carries less narrative weight. Without narrative, flavor has less amplification. Even branding and language influence perception. Descriptive labels activate associative networks. Calling something wood-fired coastal bread engages imagery and expectation differently than calling it bread. Those expectations alter perceived flavor intensity. Location supplies narrative automatically. There is a deeper mechanism beneath all of this. The brain operates through predictive processing. It continuously generates models about what will happen next. Sensory input is compared against prediction. When prediction and input align, perception feels smooth and satisfying. When they misalign, friction appears. In a novel place, prediction error is higher. The brain pays more attention. Food becomes part of that learning process. Attention increases sensory resolution. At home, prediction error is low. The brain economizes. Sensory processing becomes compressed. The food did not change. The model did. There is also cultural encoding. Taste preference is partially learned through exposure. Environmental cues signal authenticity. A dish eaten within its cultural context aligns with learned associations, architecture, language, sound, climate. These cues reinforce the brain's interpretation that the food is correct. Remove those cues, and subtle dissonance appears. The sensory system detects incongruence even if you cannot articulate it. Flavor depends on coherence. Temperature outside the body also plays a role. Eating warm food in cold weather intensifies perceived comfort because thermal contrast activates somatosensory pathways linked to relief. Eating cold food in hot weather does the same. Place alters bodily state. Bodily state alters taste. Fatigue, stress, and circadian rhythm further modulate perception. Cortisol levels influence reward sensitivity. Time of day affects insulin response and taste receptor sensitivity. A meal eaten during relaxation at sunset in a new city is processed differently than the same meal eaten hurriedly between obligations. The brain integrates internal state with external input. Flavor is the result. There is an assumption that taste resides in ingredients. It does not. Ingredients provide chemical signals. The brain interprets them using context, memory, expectation, environment, social signals, and internal physiology. Location changes all of those simultaneously. So when the same food tastes better somewhere else, nothing mystical occurred. No secret ingredient was added. What changed was the system constructing the experience. The environment recalibrated attention. Novelty elevated dopamine, sound altered interpretation. Memory encoded emotion. Expectation shaped reward. The dish remained constant. The model did not. This reveals something quiet about perception. You do not experience food directly. You experience a prediction stabilized by context. Change the context, and the prediction shifts. The shift feels like flavor. It is not the place that adds taste. It is the brain that completes it. And once that becomes clear, flavor stops being a property of the plate. It becomes a property of the system experiencing it. If you enjoy learning facts that quietly change how you see the world, subscribe to Do You Notice? Because next time, we'll uncover something you've been overlooking.